Welcome back. In this video, I will introduce the functionalities of link layer and I will go over what is called framing. Framing refers to methods that are used to demarcate the beginning and ends of the data blocks on a link. By the end of this video, you would know what are the main functionalities of link layer and would also know how are the boundaries of a data block specified. Data link layer is the second layer of network architecture. This layer is concerned with the question of how to send packets over a link. In a packet-switched network, nodes exchange data blocks and not stream of bits. Link layer is concerned with reliable exchange of data blocks between two nodes. Connecting two nodes with a link for exchanging messages involves several steps. The first is encoding and modulation. We need to encode bits onto transmission medium so that they can be understood by the receiving end. And we saw the methods for encoding and modulation in a previous video. The next is framing, where we have to delineate the sequence of bits that are transmitted over the link into complete messages that can be delivered to end node, and that's the topic of today's video. Then is error detection. We need to detect transmission errors that occur and we need to take appropriate action for those errors that have occurred in messages. And then is reliable delivery. That is, we need to make links appear reliable despite these transmission faults. And lastly, medium access control that applies to multi-access links. Remember, in multi-access links are shared among several nodes, and therefore we need to decide which nodes get access to medium when in the case of these multi-access links. So we are going to, as I said, we have discussed encoding and modulation in a previous video. We will discuss framing today, and then we will discuss these three topics in the next videos. Although physical links carry bit streams, in packet-switched networks, nodes exchange blocks of data and not bit streams. The block of data at link layer is called frame. It's the network adapters which we discussed in a previous video. They're also called NICs or network interface cards. It's the network adapters that enable the nodes to exchange frames. As Peterson and Davy put it somewhat poetically, bits flow between adapters, but frames flow between hosts. To send a frame to node B, node A would instruct its adapter to fetch the frame from its memory and send it over this link. This results in a sequence of bits being sent over the link. On the receiver side, the adapter on B collects the stream of bits arriving on this link and stores the frame in B's internal memory. The main problem for node B's adapter is to determine where the frame begins and where the frame ends. And this is called the framing problem. We will discuss three different approaches for framing. They are byte-oriented framing, bit-oriented framing, and clock-based framing. We will begin with byte-oriented framing. Byte-oriented framing is an old method that originated in connecting terminals to mainframes in 60s. Byte-oriented framing views each frame as a collection of bytes. As you know, a character is also one byte, so it's also referred to as characters. And byte-oriented framing is used in it was actually first used in a protocol called Bisync, stands for Binary Synchronous Communication Protocol, which was developed by IBM in late 60s. It was also used in another protocol called DDCMP, stands for Digital Data Communication Protocol, which was developed by Digital in 1974. Currently, this approach is used in point-to-point protocol. We will discuss all three protocols. Bisync uses Sentinel approach. In this approach, special bytes known as sentinels are used to delineate a frame. The frame format for Bisync is shown here. Remember that these numbers at the top represent the length of these fields. So a Bisync frame begins with two syn or that stands for synchronous idle characters. They're both 8 bits. These syn characters are followed by another character called start of header or SOH. SOH is followed by the data portion which is contained between these special sentinel characters. STX stands for start of text and ETX stands for end of text. And at the end of the frame there is a 16-bit CRC. We will learn about CRCs in a later video. CRCs are used to detect errors in a frame. The problem with this approach is that this ETX character may appear inside the data body. And when that happens, it will cause the receiver to assume the end of data and treat the next 16 bits as CRC. And suppose this particular byte inside data is the same byte as ETX, then what will happen is that the receiver is going to treat the next 16 bits as CRC and simply discard the rest of this frame. And obviously this CRC is going to not match with the data that was sent, and this frame is going to be discarded. And so this problem is solved using a method called byte stuffing. We use another special character, right, which we call escape character, data link escape. Along with ETX, whenever ETX appears inside data. Here is how this byte stuffing is going to work. So suppose we have this ETX byte inside the data. And so the receiver side, what is going to happen is that DLE is going to be repended whenever ETX appears, and what goes on the link is DLE followed by ETX. On the receiver side, the receiver would always strip off the first DLE, and so what the receiver is going to pass on is this DLE is stripped and just ETX. Now the question is, what happens when we have DLE itself in data, right? Because as I said, the rule is that the receiver is going to strip off the DLE whenever it appears and just take the byte after that. And so when DLE appears, it's sent as 2 DLEs. And receiver, as I said, is simply going to strip off the first one. And so what gets passed on is what was sent. Another problem with this approach is that this character ETX itself may get corrupted. And if that happens, then the receiver won't be able to tell that's this end of the frame. Right? So it's just going to keep reading until it sees another ETX somewhere. And that would result in back-to-back frames getting discarded. This is called framing error. Point-to-point protocol, or PPP, is used to carry IP packets over point-to-point links. PPP also uses Sentinel approach for framing. This is a PPP frame format. The flag fields at the beginning and at the end of the frames contain the Sentinel character. In the case of PPP, this is 0 followed by 6 ones followed by another 0. PPP uses 0 followed by 5 ones followed by 0 followed by 1 as escape character for byte stuffing. These address and control fields contain default numbers, so they are not really interesting. This protocol field is used for demultiplexing as well as to send control messages, which we'll see in just a bit, called link control protocol. And the payload in PPP is by default 1500 bytes, but this can be negotiated. Again, this protocol LCP is used to negotiate that. And the checksum is by default 2 bytes or 16 bits, but it can be negotiated to 4 bytes. PPP, as I said, uses another protocol called link control protocol for carrying out these negotiations. These LCP messages are sent encapsulated within PPP frames, where this protocol field is set to indicate that the frame contains LCP message. LCP is also used to establish new links when one end or both ends boot, right? So one of the ends is going to discover a new link when it receives a signal from the other side. And at that time, LCP is used to establish a new link between these two endpoints. Byte counting approach is an alternative to Sentinel approach in byte-oriented framing. Byte counting approach is rather simple. In this approach, the payload size is indicated in the frame header itself. This is a frame format of DDCMP that uses this byte counting approach. Here it uses a 14-bit field to indicate the size of the data body. And this number indicates the number of bytes that is contained in the data body. The main problem with this approach is when this count field gets corrupted, back-to-back frames have to be discarded until the receiver would recover and detect these SYN symbols again. Bit-oriented approach to framing is used in high-level data link control protocol, or HDLC for short. HDLC is an ISO standard that was derived from IBM's protocol called Synchronous Data Link Control Protocol, or SDLC for short. This is a frame format of HDLC. As you can see, the beginning and the end of the frame are marked by this special sentinel character 0 followed by 6 ones followed by 0, which is same as the sentinel that's used in PPP. In HDLC, this sentinel character is sent continuously when the link is idle, and this helps in keeping the clocks synchronized. Here again we have this problem that this sentinel character can appear anywhere inside body, right? So this could be the 0 followed by 6 ones followed by 0. And so what can we do? Now note that we are not using byte-oriented approach, but we are using bit-oriented approach, in which the protocol sees this body as sequence of bits. And therefore this flag can appear across byte boundaries. So maybe these first three bits are part of one data byte, and these another 5 are part of the following data byte. HDLC solves the problem of the flag appearing inside the body of the message by an approach that's analogous to what we saw as byte stuffing. What it does is it inserts a 0 anytime it sees 5 consecutive ones in the body of message, right? And that's called bit stuffing. And so suppose we have this example of 0 followed by 7 ones followed by 0 appearing in the message. And so after bit stuffing, this becomes 0 followed by 5 ones followed by a 0 followed by 2 ones and a 0. On the receiver side, if it sees the 6th bit as 0, right, after 5 consecutive ones, it treats that 6th bit, that 0, as the stuffed bit, and it will discard that one. So on the receiver side, this is going to be 0 followed by 5 ones, and then there is a 0 which the receiver will discard, and then 2 ones and a 0, then something else, also something else. And so basically what was sent in the message is what is passed on as the message. There's another example. So it may be that there actually is a 0 after 5 ones in the message body. However, because of this rule that the receiver will always discard this 6th bit if it is 0, counting that as a stuffed bit, the sender must insert an extra 0 over here. And so what the sender is going to do is it's going to send this stuff that is before followed by 5 ones, and then 2 zeros, and then 1 and a 0. And again, the receiver will discard this 6th bit after 5 ones, and then keep the rest. And so basically again it matches what was sent. Okay. But the receiver also has to deal with the fact that it may receive flag, right, somewhere. So at the end of the frame, it's going to receive that flag that has 0 followed by 6 ones followed by a 0. And therefore, if the 6th bit is 1 after 5 consecutive ones, and the 7th bit is 0, then it will treat that as end of frame flag. However, if the 6th and 7th bits are both 1, right, it will treat that as error, and it will discard the whole frame and wait for the next start of frame flag. An undesirable effect of both bit and byte stuffing is that the frame size becomes a function of data content. Sonnet, which stands for Synchronous Optical Network, was developed by Bell Corps in mid-80s and has been adopted as an ITU telecom standard for digital transmission over fiber optic networks. It uses clock-based framing. The terminology is not a standard one, but that's what the textbook uses. And it uses this clock-based framing in the sense that the frame duration is fixed at 125 microseconds. A Sonnet frame contains 9 rows of 90 bytes. And so all in all, this is 810 bytes. Out of that, the first 2 bytes indicate the frame start, and the first 3 bytes of each row contain control data, and that leaves 783 bytes for payload. Sonnet provides both framing as well as encoding. In Sonnet, data is scrambled before sending, and by scrambling, what we mean is that the data is XORed with a known 127-bit pattern, right? And this bit pattern has enough transitions. And this is done because this scrambled data is encoded using NRZ. Now remember, NRZ suffer from baseline wander and clock recovery. And the purpose of this scrambling is to fix both of these problems. The receiver recovers the message by again XORing with the same 127-bit pattern that we use for scrambling. Let's say D is the 127 bits of message, and then we XOR with this 127-bit pattern for scrambling, and then the same 127-bit is used on the receiver side. And so after all these XORs, what we have is D XOR S is 0, and so we get D back. Sonnet offers several data rates starting from 51.84 megabits per second to 2.4 gigabits per second and higher. The Sonnet frame I described in the previous slide is called STS1 frame, and recall it had 9 rows of 90 bytes, and that's 810 bytes. These STS frames come with a number, STS followed by a number. So STS-N frame size is going to be N times the STS1 frame size, which is 810 bytes. Since Sonnet frames last for 125 microseconds and STS-N frame sends N times the data as STS1 frame, and therefore it gives N times the data rate of STS1 frame. And so here you can check that STS1 frame gives 51.84 Mbps, and therefore STS48 should give you 48 times 51.84 Mbps. And for STS1, the data rate is 51.84 because we are sending 810 bytes. So 810 times 8 bits, all in 125 microseconds. And after calculating this, you will get 51.84 Mbps. And STS n frame usually interleaves the bytes of n STS1 frames just to pace the delivery of frames at the receiver. However, there exists concatenated frames standard where STS1 frames are sent back to back as it's shown here, and those standards go by C after the number. So an STS-N standard can be thought of as N 51.84 Mbps pipes, whereas STS-N-C can be thought of as 1 N times 51.84 megabits per second pipe. One final thing to note about Sonnet is that in Sonnet, payload can span multiple STS1 frames, and control bytes would indicate the start and end of a payload in such cases. To summarize, data link layer is concerned with sending data blocks over a link, and at link layer these data blocks are called frames. Framing is the process of marking the start and end of a frame, and we saw three different approaches of framing. One was byte oriented, the second one was bit oriented, and third was clock based framing. Sentinel based framing methods need to take care of the fact that these sentinel bytes may appear inside the data body, and therefore they need to use byte or bit stuffing as appropriate. Lastly, Sonnet uses multiples of 800 byte STS frames. A Sonnet N standard would send N times 810 bytes in 125 microseconds. A Sonnet provides both framing as well as encoding. The material that I covered in this video is discussed in detail in Peterson and Devi, Chapter 2, Section 3, and in Tenenbaum and Weatherall's book, Chapter 3, Section 1. Here is a short quiz for you. Find out which of the following statements are correct. You might want to pause this video. The correct options are A, B, D, and F. A, that says link layer is the second layer of network architecture. That's correct. B says exchange of frames between two nodes connected by a link is the function of link layer. That's also correct. C says in Bisync, DLE ETX after byte stuffing is sent as DLE ETX. And actually, remember the rule is that DLE is escaped. So DLE gets sent as DLE. And ETX is also escaped, so it's going to be sent as DLE followed by ETX. Right, so this is wrong. ETX DLE after byte stuffing is sent as DLE ETX, DLE, that's correct. Just slight variation on what I just showed you. E is wrong. In Sonnet, the encoded data is sent using NRZ, not NRZI. And F is correct. Sonnet frame sizes are integral multiples of 810 bytes. That's all in this video. See you next time.